Warning: hydrochloric acid and nitric acid are corrosive. Palladium chloride and triphenylphosphine may be irritating. Parts of this experiment involving toxic gas generation should be performed outside or in a well-ventilated area. Hi guys, here is MIH. Palladium is a transition metal element known to have very powerful, almost magical properties on catalyzing a surprisingly wide range of reactions, from those used at million-ton scale in chemical plants to ones appearing in niche laboratories for synthesizing new drug molecules. Today we're going to explore the synthesis of palladium chloride and bis-triphenylphosphine palladium chloride, two very useful compounds that are themselves catalysts and can be used as precursors to other important catalysts. My source of palladium is this piece, roughly 3 cm by 2 cm and weighing 1 gram. It is actually a generous gift from one of my friends, bought from an element collection store at around $60 or 400 RMB, which is about the same as the palladium market price at that time. By the way, the price of palladium and its compounds had been rocketing since the past 10 years, and at chemical companies, our two target compounds cost significantly more than the pure metal based on the palladium content. Still, most researchers and labs I know of pay for this markup because they have much more funds to buy chemicals with and they don't have many valuable times to spend on making them like what I'm doing in this video. Anyways, I cut the piece into two and take the smaller portion, weighing 0.43 grams. Weighing small masses on a not-so-accurate scale here is usually bad practice, and I should use my jewelry scale that can go down to milligram accuracy, but that scale ran out of power, and I'm not doing any very precise work here yet. As I weighted the palladium, I placed a beaker with 20 ml of 20% hydrochloric acid on the hot plate and brought the acid to a boil. Now the palladium piece is placed into it, and a watch glass is placed on the beaker to limit evaporation. The palladium surface is still shiny and no reaction occurs. However, when I add 6 ml of 60% nitric acid, the solution yellows in an instant, the palladium surface dulls, and an orange haze forms on top of the acid. Nitric acid reacts with hydrochloric acid to form yellow nitrosyl chloride, which dissolves in the acids, and it, along with remaining nitric acid, oxidizes palladium to brown palladium chloride and nitrate, forming orange nitrogen dioxide gas. Just as I finished the sentence, the color of the solution darkens significantly due to dissolved palladium, and the nitrogen dioxide haze is easily visible. Just as a side note, mixing the acids according to the aqua regia ratio, or 1 part nitric acid to 3 part hydrochloric acid, is only a good approach when working at this small scale. For dissolving tens or hundreds of grams of palladium or other precious metals, the nitric acid shouldn't be added all at once, but rather by small portions of 5 or 10 milliliters over the course of a few hours. This is because excess nitric acid forms more nitrosyl chloride gas that can boil out, essentially consuming away expensive nitric acid that is not actually oxidizing the metal. 20 minutes later, the reaction mixture had darkened significantly, and its color closely resembled boiling soy sauce, but a little bit more reddish. The orange haze is still seen, meaning that nitric acid isn't yet depleted, and the mixture should be allowed to react for longer. We avoid adding too much nitric acid to avoid dealing with lots of nitrosyl chloride later on, as we have to remove them to ensure our palladium chloride is free from nitrate. Around half an hour later, the remaining palladium floats on top. It's quite interesting to see that it still retains the original rectangular shape, but it has now become incredibly thin. You can literally see it dissolving in the acid. Took us an hour, and we've turned our $25 palladium to this beaker of corrosive soy sauce. But of course, we're not done yet. I add 20 ml of 20% hydrochloric acid to the beaker and transferred everything to a petri dish for evaporation. This part is done outside as it emits lots of hydrochloric acid and nitrosyl chloride vapors. The higher wind speed outside also makes evaporation faster. Here we are destroying remaining traces of nitric acid by adding extra hydrochloric acid to form nitrosyl chloride that is boiled away. The purity of palladium chloride is essential to sensitive catalytic reactions, so I want to ensure that it is free from any nitrate. Similar operations are done routinely when producing chloroplatinic acid from platinum. As a side note, if you don't have lots of hydrochloric acid on hand to perform this evaporation step, using hydrogen peroxide in place of nitric acid lets you skip this part. The drawback is that the initial dissolution is slower, since hydrogen peroxide decomposes quite rapidly in boiling solutions, while nitric acid decomposes slower. As the palladium solution concentrates to a syrup-like consistency, I add another 20 ml portion of 20% hydrochloric acid and repeat the evaporation process. Usually this evaporation is repeated for 3 times or until no more brown fumes are seen, but I used only a slight excess of nitric acid to the palladium, so evaporating 2 times is fine here. Additionally, impurities in the hydrochloric acid also concentrate in the palladium solution, so it is best to avoid evaporating too many times. I transferred the palladium solution to a beaker and continued heating until drying. Be sure to heat the mixture for a while after dry to drive all water and acid off, and there we have it, some red-brown palladium chloride. I scraped it off the beaker using a spatula and found its mass to be 0.68 grams, which gives a 95% yield. This high yield is typical for these metal dissolving reactions, and losses are likely due to the repetitive boiling and transfer processes. Also, since the balance is not very accurate, the yield may also be close to 100%. Now that I have palladium chloride, I'll synthesize bis triphenylphosphine palladium chloride from it. With its triphenylphosphine ligands being the most common phosphine compound encountered, this molecule is the most basic one among this class. Far more complex phosphine ligands, each with an engineered spatial structure to enhance the rate of specific reactions, can be used in place of triphenylphosphine to synthesize an infinite number of palladium complexes specialized to catalyze all kinds of reactions. For example, DPPF and DTBPF for Negishi and Suzuki couplings, S-phos for Suzuki coupling of rather unreactive aryl chlorides, and X-phos for Buchard-Hartwig emanations, just to name a few. The ligand surrounding palladium isn't limited to phosphines, and even more exotic palladium complexes such as tris dibenzylidine acetone dipalladium 0 and PD-PEPPSI-IPR are also very important in coupling reactions. This field of cross-coupling and organometallic catalysis is so interesting that I may devote a series of videos towards it in the future, and I surely want to hear some suggestions about what I could include in the series. Anyways, back to the experiment. The standard way of preparing bis triphenylphosphine palladium chloride requires heating triphenylphosphine and palladium chloride in some kind of nitrile solvent, such as acetonitrile or benzonitrile. Since I don't have these on hand, I'm taking a new approach that uses ethanol instead. I weigh out 0.37 grams of our freshly made palladium chloride and dissolve it in 3 ml of 20% hydrochloric acid. The exact quantity isn't critical, but using less acid is generally preferred. The beaker is slightly heated to dissolve all palladium chloride, which reacts with hydrochloric acid to form tetrachloropalladic acid. Meanwhile, 1.15 grams of triphenylphosphine, or 2.1 equivalents to the palladium chloride, is dissolved in around 20 ml of ethanol. Again, the exact quantity is not critical. The mixture is heated to boiling and the triphenylphosphine crystals rapidly dissolved. Now, the tetrachloropalladic acid solution is added to dropwise. Immediately, a vibrant yellow precipitate forms, which is our target product, bis triphenylphosphine palladium chloride. Other phosphine complexes of palladium such as PD-DPPFCl2 can also be prepared by this method, using suitable quantities of the ligand. The main difference between this method and the usual method is that the product forming here is a very fine powder that may be of lower purity, while the complex crystallizing bar nitriles forms large crystals of higher purity. The purity here is satisfactory for many applications, but if you're really that picky, recrystallization would easily purify it into large crystals. After all of the tetrachloropalladic acid is added, the mixture becomes a yellow slurry resembling a cup of mango milkshake. The product is vacuum filtered through a glass funnel, washed with ethanol, and scraped down after drying. The yield is 1.38 grams, representing a percent yield of 94%. As some product is still stuck to the funnel, the actual yield should also be close to quantitative. I'll use the complex in a future project on a novel zinc-catalyzed Kumada Negishi coupling. See you soon!